my second year of ITAMP fellowship, and I enjoy doing research ranging from quantum criticality to topological states of matter to many quantum chaos. But today I'll be telling you about quantum scars and regular eigenstates that we found in a chaotic spinor condensate, together with Bertrand Everard, who is a postdoc at ETH Zurich, Andre Pizzi and Simos Mistakidis, who are here, postdocs at Harvard.
Yeah, by the way, there's a message from Eisenberg.
Okay. Sound is always good now. Okay, great.
Mute.
I don't know how that happened. Okay, all right, great.
It should have. Oh,
It's working. All right, great. Okay, so I'll first start with the definitions. So quantum scar actually is an old concept that goes back to 1984 to Heller's famous paper on quantum billiards. More specifically, a quantum scar is an eigenmode with a higher probability density in the phase space, like you see here. And that higher probability density is actually accumulated in the vicinity of a classical trajectory, classical periodic orbit, which is unstable, okay? And by unstable periodic orbit, what I mean is when you calculate the Lyapunov exponent of this trajectory, you get a finite Lyapunov exponent, positive Lyapunov exponent. So, yes. So if the quantum scars are well defined, they're well defined objects in the phase space, and there are certain criteria for them. First of all, the model needs to have a phase space, right? And then as I give you the definition, this quantum eigenstate needs to have this higher probability density around the periodic orbit. But importantly, the scarring classical orbit needs to be unstable and embedded in a chaotic region, okay? And as a result of these criteria satisfied, we see revivals of state fidelity in time. Okay, I guess I am standing in front of my slides.
yeah.
Okay. Oh, yours, I see. Okay, thank you. Yes, it's working. Thank you, guys. Yes. Okay, so this is what a quantum scar is, quickly in a nutshell. And now we have this new concept that was introduced to our vocabulary in the last few years, quantum many-body scars. They were first seen in the experiment on the Rydberg atom array and as a robust oscillations in the domain wall density. Okay, and quantum many-body scars are actually non-terminal states embedded in the spectrum, like you see here, for example. See this one. Okay, yeah, like these states that are separated from the rest of the spectrum. And this experiment later was elucidated in this work here in terms of a model called PXP model. PXP model is a spin model that integrates into the Rydberg blockade constraint into the system and can explain why there are these oscillations in the experiment. So there are actually, it's still on the quantum many-body scars are still going on research, and there are certain classes of them, like there are three total classes, and even though PXP model is the most famous one in all of them, there are multiple models that goes under all these like classes of QMBS. But then when we look at them, actually there's a certain common denominator that brings all these works together. So I'll try to actually like tell about these criteria here. First of all, we find them to be low entropy, non-chaotic, and eigenstate terminalization hypothesis violating many-body states. And ETH, eigenstate terminalization hypothesis, what I mean is they're not terminalizing states. Importantly, they're negligible in the thermodynamic limit. So we can see an example of this based on the PXP model while the dimension of the Hilbert space is exponentially increasing in system size or the atom number, the number of quantum many-body scars are changing linearly. So then you can see in the thermodynamic limit they're negligible. Also, depending on the model, they could be equally spaced across the many-body spectrum. And again, you can see this here for the PXP model. Not every QMBS need to be equally spaced. But if these criteria are satisfied, we can see the revivals in the state fidelity and the robust oscillations in the observables when the dynamics is initiated at an experimentally feasible state, like a product state, for example. Okay, so probably like anybody who starts doing research here on this area would ask the question whether there is a connection between quantum scars and quantum many-body scars, as the name implies. And is there really a connection between them? So in an attempt to answer this question, there were two works, and both of them are in PXP model. So we have some partial information about that. And in this work, Wen-Wei Ho and others try to answer this question based on the PXP model by coming up with this variational ansatz on a low entanglement states. Okay, and this is the phase space that they come up with based on this let's say formalism. And this is basically an effective phase space. The reason is PXP model itself is a fully quantum model and it doesn't have a classical limit. So it normally doesn't have a phase space. So they needed to come up with this method. And they found here an unstable periodic orbit, the red one that you see here, associated with the quantum many-body scar. But it was actually embedded in a 2D regular phase space, which is a non-chaotic phase space. So following this work, Michaelidis and others worked on more generic embeddings, again on the variational ansatz approach of the PXP model, and they looked at higher dimensional effective phase spaces. And here you see a three-dimensional version, and they found mixed phase spaces. And particularly, they actually found that the quantum many-body scars are associated with a stable periodic orbit in a 3D mixed phase space in this case. So in particular, these stable periodic orbits in the regular regions of the mixed phase space. So conclusion to date, actually, there is no quantum many-body scar corresponding to a quantum scar in a phase space. So the quantum scar and regular states, these are well-defined concepts in a phase space. And we expect quantum star to be associated with an unstable periodic orbit that has a positive Lyapunov exponent. While the regular states, they're associated with stable periodic orbits, and stable periodic orbit, what I mean is the Lyapunov exponent is 0. So these are very well-defined concepts. Well, QMBS, we really look at in a many-body spectrum, right? So, and there is no correspondence yet between them. The second conclusion to make here is that the relation of QMBS to quantum scars and regular states remains unclear. So here in this talk, I'll try to address this second point from a fresh perspective through chaotic spinor condensates. But before actually getting into the chaotic spinor condensate, let me introduce the spinor condensates first. These are spinor condensates are experimental platforms that are used to explore quantum many-body physics all around the world at this point. And when we start working with spinor condensate, first of all, we have in the Hamiltonian, we have the kinetic part and the potential part and the interaction part. Take note that we are actually working with a spin 1 spinor condensate, so the magnetic quantum number changes from -1 to 1. In the interaction part, we have symmetric and anti-symmetric parts. These symmetric and anti-symmetric parts have strengths that depends on the scattering lengths of the colliding pairs. For rubidium and sodium species, these are the particularly most used atomic species in the spinor condensate platforms. We have C0 prime, so much bigger than C1 prime, which justifies what's called single mode approximation, SMA. So in the single mode approximation, the spatial part of the wave function is found to be homogeneous, And as long as this approximation holds, we can basically turn this interaction part of this spinor Hamiltonian into a simple spin-1 Hamiltonian. Okay, and then when we have the spin-1 Hamiltonian, we can write this down in the Fock basis. And in the Fock basis, we end up having these simple interaction, density interaction part, and then the spin mixing interaction part, which basically really mixes the spin 0 to spin 1 and -1 and the other way around. Okay, the SMA, the single mode approximation is actually a versatile approximation. There are multiple experiments in the last decade that use the SMA to describe the experimental findings. So it is actually a good approximation to make and good model. Okay, but the model itself, the spinor condensate, is integrable. And we want to study a chaotic system. So we're going to break the integrability by introducing mode mixing term to it. So this is our spinor Hamiltonian. And let's acknowledge that there is generally a magnetic field in the z direction in these systems, which introduces the linear and the quadratic Zeeman terms. And we add two rotating fields here at the frequencies that are resonant with the 0 and ±1 atomic transitions, which is HR here. And we do a rotation around the z-axis, a unitary transformation. And after doing this, we end up with this effective interaction Hamiltonian. Here, the H int stands for this simple density interactions. And one condition, if we basically have a large magnetic field, then we can integrate over these fast oscillations and end up with this effective Hamiltonian that has an interaction part and the mode mixing part that is breaking integrability. So from now on, basically, we'll be sticking with this experimentally feasible the chaotic spinor Hamiltonian. And unless otherwise, I'll be sticking with this P is equals 0.05 while fixing the spinor condensate to a ferromagnetic condensate. Let me note that this model is interesting in the sense that it has a diverging density of states in the middle of the spectrum. So it actually helps initiating the chaotic behavior in the middle of the spectrum. So that's one of the reasons why we stick with this. We first look at the phenomena entropy of one-body density matrix. And this basically helps us to understand the entanglement of one atom with the rest of the ensemble of atoms. And we see this entropy plot. So there are two things to note here. The first one is that most of the states are in this maximum entropy band. Okay, while the sum of the states are actually have this like structure. They have some regular structure to them. Okay, so the first thing that we look at their energy level statistics, and specifically the nearest neighbor here. When we look at this states within near the high entropy band, we see them they're actually satisfying the Wigner Dyson statistics, meaning that they are chaotic states. And when we look at the other states, as regularly organized states, they actually show Poisson statistics, meaning that they seem integrable states. So from now on, I'll be calling these band of states here chaotic bands because it shows chaos, and then the other ones are regular states. But I'm going to justify the names more as we go on. So the next thing that we want to look at whether these states satisfy or violate ETH, eigenstate thermalization hypothesis. For these, we need to set the observable. First, we choose as the observable is the number density of the atoms with the 0 spin component, which is really the one that's mostly measured in the experimental platforms. There are two criteria that needs to be satisfied for ETH. The first one is about the diagonal elements of this observable. They basically need to change smoothly with the energy eigenvalues, while the second one is about off-diagonal. The off-diagonal elements of the observable that we're looking at needs to be negligibly small compared to the diagonal elements of them. And if these criteria are satisfied, then we know that the local operator N0 is going to relax this thermal value dictated by the microcanonical ensemble that we constructed in a narrow energy window in the spectrum. Okay. that also means that just when any one state that we take in the energy window is going to be enough to describe the thermalization properties of the system. So we will first look at some indicators for the first ETH criteria. Here is our, I can say, expectation values. The first criteria that we look at is the support. So the support is basically the difference between the maximum, I can say, expectation value and the minimum expectation, I can say, expectation value. And we expect this support indicator to decrease, vanish to zero as the system size increasing. So let me note that it is actually sensitive to the outliers. So then we actually fix the we set a fixed energy window as the system size increasing. Yes.
So just making sure. So when you say as system size increases, you have this spin model, like this total spin model.
Yes.
In fact, there's log3 means like an all-to-all coupled model.
Indeed.
And then it's kind of like you're now increasing the size of the total spin.
No, we are increasing the particle number,
Which increases.
which increases the size of the spin. Yeah, you can look at that way.
And so you're fixing like the total spin of the system and looking within like the dynamics within the manifold of total spin being 10.
I think if you look at it from the spin picture, yeah, you can see it that way. But really, and physically, what you do is you increase the number of atoms. So that's basically the system size here because it's an all-to-all system. There is no dimension. Go ahead. Okay, so the support, and then the next criteria is that noise. So noise measures how much the, I can say, expectation values are differing from the microcanonical ensemble prediction. Okay, and that's average over or entire narrow energy window in the spectrum. And the third one is the, I can say expectation value differences. These are the nearest neighbor differences and average over again the window. So first we look at the regular band, and we see all of these indicators are staying flat as we increase the atom number. So that means the regular band is not satisfying the first ETH criteria, while the chaotic band does show an overall decreasing trend as the system size increasing. So from here, we can say that the chaotic band indeed seems to be satisfying first criteria. But next, we look at the second criteria. The second criteria says that long time average of temporal fluctuations in this eigenstate expectation values should vanish. And this is what that fluctuation is. We can see that this fluctuations needs to be bounded by the maximum off-diagonal element in our energy window. So if we actually look at how these are scaling with the system size, we can have an idea about how the fluctuations will decrease. And this is what we see for the chaotic bands. They indeed tend to be decreasing as the system size increasing. But the second part of the second criteria is actually how the off-diagonal elements are changing with the energy differences that you see here, EQ over minus EP minus EQ. So specifically, it says that this should be a smooth function. And when we look at the chaotic states, we indeed see that the states are accumulating around a line. So that's this red line here is a moving average of it. While this is in contrast with the regular band, which is really scattered around like the machine precision here. So from here, we can say that the chaotic band states are indeed like satisfying the ETH, while the regular bands are violating it. Okay, now let's look at the dynamics. When we initiate the dynamics at a Fock state, which is a product state of this property is here, we see that this kind of state actually overlaps with the regular band states. And in accordance with that, actually we see the very well like robust, well-defined oscillations in the population, while the fidelity is almost perfectly reviving back. And this is in contrast with a state the state that actually overlaps with the chaotic band there. You can see that kind of dynamics actually will thermalize the microcanonical ensemble prediction, and there will be no revivals. Okay. So now let's remember the criteria of QMBS. the low entropy non-chaotic ETH violating many-body states we have for the regular states. Depending on the model, they could be equally spaced across the many-body spectrum, which we do have some approximate equal spacing indeed for the regular states. And as a result, we do have actual revivals in the state fidelity, and observables have this robust oscillations. This is the result, but are they really negligible in a thermodynamic limit? That was one criteria of the QMBS, right? We see that this is not the case. The ratio of regular states to Hilbert space dimension is fixed as the system size increasing. Let's make a comparison with the PXP model, QMBS. The system, as I said before, the system dimension of the Hilbert space is exponentially increasing, while the number of QMBS is linearly increasing, making the QMBS negligible in the thermodynamic limit. Whereas in our case, the regular states, both of them actually quadratically increasing in system size. And it doesn't actually change, the scaling doesn't change when we double the P, even though the values really become very small. So as a result, the regular states are not negligible in the thermodynamic limit. Yes?
Where is the second? It's equal spacing.
That depends on the model, really. So for PXP model, they are equally spaced. And in fact, there are certain there's a certain formalism called spectrum generating algebra, which you can create these equally spaced states by applying the operator, scar operator. So for certain QMBS, there is that criteria there.
Equal space like the harmonic oscillator.
Yeah, kind of, but actually you can think of this as like, you see perfect revivals, right? The fidelity revivals. That is actually helpful for that, because then your initial state is overlapping specifically with this equally spaced states, which gives rise to these perfect revivals. Yeah. So you won't actually see that perfect revivals for any kind of quantum many-body scar in the literature right now. Right? There are many different quantum many-body scars. Okay, so, but this suggests
Can you give us a sense of like what's the nature of these states? Like how should it, like in the PXPs, like it's C2, these two states, it kind of oscillates between like one the antiferromagnetic configuration and another. In the dynamics of these states, like do you have a feeling? Can you tell us a little bit more like what the states just look like? Yeah, you mentioned these Fock states, but it seems like you have n squared Fock states. So how should I think of it?
That is really the scaling, the n square. So there is like a non-universal coefficient in from. So they're actually really, their numbers are small. They're not actually large numbers. So first, let me make that note. But on top of it, there are indeed like these specific states here. They indeed have this like Fock state kind of nature to them. Maybe I can tell you more about this if I have time at the end of it, or we can also chat offline. Yeah. So, all right, as a result, this suggests a signature in the mean field limits, which we study next. Okay, so our model has a well-defined classical limits and mean field limits. So this is our Hamiltonian, right? So we start by writing SU3 coherent state, the zeta here. Okay, that again, the n runs here. The n is the magnetic quantum number that runs from -1 to 1 or like the creation operators for each quantum number. So maybe it's easier to see this when we write the coherent state in the spinor basis. And normally we have 6 independent variables, but through the normalization condition and the irregular global phase, we can actually reduce this to 4 variables, which is n0 is the number of atoms, the density, the number density of the atoms and the 0th spin, while the m is the magnetization density. Okay, and then the eta and theta are the phases related to the creation, the spin 1 and -1, the particles. Okay, so we can calculate the mean field energy per atom based on this the coherent state. And importantly, we can write down a Lagrangian and then solve the Lagrange equations to get the equations of motions. So what we see here, we have 4 equations and 4 unknowns. So we have a 4D phase space. One note, however, that this 4D phase space reduces to 2D at a special point when m and eta is equal to 0. So that means At this exact point, the equations are analytically solvable, but if we're not at the special point, then the equations are non-integrable. Basically, they need to be solved numerically. So that also means that our phase space can support chaotic behavior, chaotic dynamics. Okay, so we first start by examining the stability of the trajectories in the phase space. So let me also make a note that this is a Hamiltonian system, so the energy is conserved. For any trajectory that you see, the energy is conserved. And specifically for this plot that you see here, we choose to have the trajectories at this energy per atom, okay, this value. But this means that when we specify 3 variables with the energy constraint, the 4th variable is going to be already determined. So when we first found this like chaotic phase space, and then an unstable periodic orbit embedded in this chaotic phase space. Okay, so we know that this is an unstable periodic orbit because its Lyapunov exponent is positive. And on top of it, we find stable periodic orbits that you see here with the Lyapunov exponent 0. So to see how this phase space trajectory is corresponding to our quantum states, we plot the Husimi Q function of eigenstates, psi n here, in the coherent state basis, okay? And we're gonna first look at the regular states projection, and this specifically this one here. So first observation that we have here, when we look at the Husimi Q projection of the state, we see that it's not filling the phase space uniformly, right? It's mostly on this area. And we confirm that the corresponding trajectory for this is a stable trajectory, and it's a quasi-periodic. And you can see the similarity between this like pattern here and the periodic orbit here. The second thing that we look at is a state from the chaotic region. Okay, and we find that this state is actually strongly scarred by the unstable periodic orbit that we just see here. So basically, we have a quantum scar here. Okay, so a note here that I'm going to make. Okay, before that, do I have 5 minutes because we start 5 minutes late?
Yes, sure.
Okay.
Maybe I can ask you.
Okay.
Ask me a question. So, what is the equations you have to?
Yes.
So the stator is the phase.
Yeah, that's the phase.
So
Yeah.
we change the phase. State solutions.
So we basically solve these 4 equations in general. So it's a non-integrable system, but we end up having trajectories in this phase space, 4-dimensional phase space. So basically, depending on the initial state, the theta is going to change for any trajectory that we end up having.
Like asking a similar question, like if you go on the next plot, how like it's like there's a bunch of dots. Like what determines them? Like
Exactly.
Okay. Yeah, maybe I actually skipped something here. What we're plotting here. So I am choosing the plot here is the Poincare section. Okay, it's a Poincare section, and specifically what it means is like we're choosing a plane at the n0 theta plane. Okay, and at the same time taking the m the magnetization density to be equal to the initial value for it. So it's a specific Poincare section, let's say, which helps us to see where is the like chaotic phase space in this mixed phase space. So we maybe like so to speak, like I can say that it is the projection of the trajectories on the specific plane that we take.
so should I think like if the way I think of the Poincare plane is like I have the trajectory 3D and I put a plane and I just keep a recording of all.
Yes, exactly. That's what we're doing here too.
But it seems like how many different trajectories are there in this plot?
There are multiple, 10 to 12 or something. Yes, so
And they're color coded.
they're color coded. The color code is a Lyapunov exponent here that you can see, so that we know that it's actually a chaotic phase space here due to the Lyapunov exponent.
But if I look on this, especially low part, what is the typical returning time for one recurrence?
Say it again.
Recurrence time for one current system. Because you have you see with this black dot, I mean, maybe you have a trajectory which often return to the same place. Yeah, it doesn't mean that it's a closed trajectory. No, because you have a chaotic stuff. Just only points return very quickly. Yeah.
So the right, you can actually see that this unstable periodic orbit here is this UPO actually lives on this plane that we are looking at, but it is actually unstable to the perturbations out of plane. That's what we find basically with the positive Lyapunov exponents. For the other trajectories here, the chaotic trajectories, actually you can look at this in 4D, but in the end, to visualize it, we need to actually like look at the planes, and then we see that like they actually go through the plane, right? With those what dots are actually. Okay, so let me wrap up. I'm gonna pass this. I'm gonna show you the scar dynamics. What we see when we look at the scar dynamics is that the observable actually shows a weak oscillations and thermalizes quickly, but the state fidelity shows like a robust first revival. So when we compare with the chaotic region, there is a difference between them. So based on this, let me say that our model has a phase space, and we see a quantum eigenstates with higher probability density around the periodic orbit. And most important, this periodic orbit is unstable and embedded in a chaotic region. And as a result of this, we see the revivals of state fidelity. So we do have quantum scars in this model. So since I don't have much time, I'm going to just flash here the all three cases. When we have regular states, if you're initiating the dynamics on a regular band or in the chaotic band, mostly overlapping with this like strongly scar regime and maybe the weakly scar regime, let's say. So based on this, we can see that there is a big difference between the regular dynamics of the regular region and the scarred region. So, and that difference is really in the fidelity. But one thing that I actually didn't mention is like whether increasing the P, the strength of integrability breaking term, could improve the signature for this quantum scars and dynamics. So, or preliminary results actually say that this is a good direction to follow. So indeed, like that we can actually make this the amplitude of the fidelity bigger than that. Okay, so we find that the chaotic spinor condensate hosts unstable periodic orbits in the phase space, which corresponds to quantum scars. We also find that they actually also host stable periodic orbits in their phase space, which corresponds to regular states. And we find that regular and scar states are different from each other, not only in the phase space, but also in the many-body spectrum. So just as a recap, we find the regular states are low in entropy, while as ETH, they show Poisson level statistics, and they have perfect fidelity revivals together with the oscillator observable dynamics. And as the name implies, they're associated with stable periodic orbits. And the scar states, as a comparison, they're high in entropy. They satisfy ETH, they thermalize and show Wigner-Dyson statistics. And their oscillatory observable dynamics decays pretty quickly compared to the regular ones and regular states. And even though there's a robust first revival, again, like the smaller amplitude and vanishes quickly. So as a last conclusion, that we see that the properties of scars in the quantum states are very different from the criteria of the quantum many-body scars. And maybe as a contrast thing to this, actually, we find the regular states are more reminiscent of the QMBS. So I thank my collaborators, Bertrand, Andrea, and Simos, and in particular Bertrand, who is the first author in our work. And our work is going to be out soon, and you can send me emails if you're interested in chatting. Thank you very much.
How would you eat in the experiment?
How do we? Yeah. Yes, that is the. Yes, that's the amplitude of the. Okay, yeah, so many things here. That's the amplitude of the. Yes. That's the rotating amplitude of the rotating field. You can see here. So by just tuning that amplitude of the rotating fields at these frequencies, we can. This is the. Yes, so this is the field in the SX and SY dimensions indeed.
If you have, I'm thinking of not necessarily many body stars, just regular stars of, like, let's say, every color.
Yes.
Describe. I think that normalization.
So, I think in phase space, when you look at a phase space, right, you do see the especially when you look at these quantum eigenstate projections, you do see actually the non-ergodicity there, right? Because it's not uniformly, the projection is not uniform over the phase space of it. So there is, in that sense, there is the non-ergodicity there. But when we look at like the formalisms like eigenstate formalization hypothesis, like these kind of criteria that we look at quantum many-body states, when we see whether the quantum dynamics is going to thermalize or not, they are indeed embedded in this, chaotic region, and we do see that they are actually thermalizing. So maybe then, like, our understanding for the quantum thermalization is not exactly the same thing with what we would expect from the ergodic theorem. So I think there is a differences there that we're seeing.
I have a question. You mentioned very important things, that quantum and many-body quantum not the same as quantum. And origin of this theoretical would be good to understand. For example, I have a quantum system which very good for semi-classical description.
That's what we have here, right?
Yeah.
There is
In this case, yeah. Maybe it's a question of many-body. Do I have a practically classical many-body system which shows some scars? Because semi-classic, very close.
So this system that we have is a quantum model, right?
Yeah.
It is a quantum model, and it's a model that describes many-body physics and experiment really well. So it's a quantum many-body model,
Yeah.
though, like, effectively, it's indeed an auto interacting gas, basically.
But it's still not semi-classical in many aspects, because cold data, I talk about Hamiltonian, you show it exists some kinetic potential and so on, yeah. I talk about trivial many-body system, yeah. Do you have a scarce many-body system which close to classical?
Well, I mean, this model still has a classical limit to it, right? So if there is a well-defined mean field limit to it. So if I take like the atom number to thermodynamic limits, that's what I'm solving here with those equations, basically mean field equations. So that's
many-body. I understood that it means that many-body important. Yeah.
Right. Okay.
What's the mechanism? How many-body influences?
So you may.
I know that it's degrees of freedom only. Yeah. Single particle, yeah, okay, scars with all.
Right.
I mean, scars, degrees of freedom.
In the end, like, I mean, the way that I am seeing is many-body because there are many atoms in it, right? So then, and we can construct a many-body state for it, which is in this particular case the Fox state.
Yeah.
Right. So in this context, it's many-body really for this model, and we're able to see like the corresponding states, that corresponding quantum states to the unstable periodic orbits in the phase space. So that's really the interesting thing here, I would say, one of the interesting things. Yeah, thank you. Yeah. Okay.